All right, so we're going to work through this practice test. Going to go kind of quickly through this, but you can use this to check your answers and maybe get a few tips along the way. So we got 1/3 x to the third, we are 3 to the x. We've got to graph this guy. So we've got to find some points here. We know that 3 to the x normally goes through 0, 1. However, this 1/3 is going to make it go 1/3 of that. All right, that's not going to work so well. Okay, so it's going to be 1/3. That's huge. Well, let's try this again. Darn thing. Well, it's going to go through 1/3 there. And then 3 to the first is usually 3, but we're going to drop that down 1/3. 3 to the second is usually 9, but 1/3 of 9 is 3. Okay, and then we have a third, a third, a third. It's going to look like this. We're going to have an asymptote of the 0 axis. And that is the x-axis. All right, so here we've got 3x plus 2. This is going to raise our asymptote up 2 there. So that's 2. And then our 3 to the x is going to go through 0, 1, 1, 3, and then 2, 9, somewhere up here and off to the left. Make sure you draw that asymptote in there. Something like that. Okay? All right, number 2 actually. Okay, so we're going to shift this here. We're going to shift it left 3. So we've got g of x, we'll give it a different name, equals, left is going to be inside the exponent here. So that's going to be x plus 3, because it's opposite from what we'd expect. It's going to go down 4, so that's going to be minus 4 out front. And it's going to reflect across the x-axis, so that's a vertical flip, so that's negative out here. For this guy, we're going to make the shift, and it's going to go right. So we've got our 3. It's going to go right, so it's going to be x minus 3. It's going to go 3 units up, so we're going to add 3 out here and reflect across the x-axis. By the way, if we reflect across the y-axis, we'd want to put a negative up here in front of that x there. Okay? Here, which one of these guys has the smallest a value? So this is just a general exponential function. So remember, the a is the initial value, and the b is the growth rate, okay, or decay rate. So if we have the smallest a value, well, a value once again is the initial value, so that would be this b, okay? So b, and it has the lowest y-intercept, okay? Which value has the largest a value? Well, that's looking for the largest intercept, and that's up here. That's going to be c. And so this is the largest y-intercept, okay? Which graph has the smallest b value? Well, small, we're talking a fraction. Fraction means exponential decay. There's only one here that has exponential decay. This is exponential growth. This is really exponential growth, but it's flipped upside down. So this is like a negative, I don't know, negative what, 2 to the x or something like that, all right? Actually, this is negative 2 to the x. This might be negative 4 to the x. All right. So anyways, so this is exponential decay. Our b value is a fraction here, so that is graph A, and because our b there would be less than 1 and greater than 0. Okay, the largest b value, well, that'd be the steepest one here. These have negative a values here. That's why they're going upside down, all right? But what we've got to do is we've got to check how quickly it's going up. Okay, this here has an a value of 3, and so the b value is a little tough to see here. This here has an a value of 4, but if we just look at the steepness, and it'd be nice if we could see another point up here, but we can't. So that one is steeper than this one, and so we're going to call that C because it's the steepest graph. Okay? Let's go on to the next page here. Section 4b, we're graphing logarithmic functions here, and so we got some transformations again. Okay, this minus 4, like usual, is going to go right 4. Inside is left or right, and this plus 7 is going to go up 7. Okay, the transformations here, we're going to go left 2, and we're going to go down 3 because of our -3 there. This is a vertical change. Outside is a vertical change, and so we got a vertical reflection and vertical stretch of 2. Okay. The domain of a logarithm is when 3x plus 1 has to be greater than 0. So we subtract 1 from both sides. 3x is greater than -1. Divide by 3. Divide by 3. X is greater than -1/3. Okay, so the asymptote is at x equals -1/3, and the domain here would be from -1/3 to infinity because it's greater than. Remember to watch out, and for some cases when you divide by a negative number here, you'll have to flip that inequality there. So, all right, describe the transformations for a log base 2, okay? So we're going to describe and graph. So we got a -2 here. -1 is going to go right 1 and up 2. So normally a logarithm curve, our plane old logarithm curve, has an asymptote of the y-axis, but this right 1 is going to give us an asymptote of 1. Okay, let's get a scale here. That's 1, that's 1 there. Okay, don't forget to label your axes somehow. That's an ugly 1. 1, 2, 3, 4, 5. How about this? Okay, so we got that. Now we're going to go up 2. So what we've got to do is this. If we go up 2, I'm going to locate this point, and I'm going to make a little mental note. I'm going to actually put a physical point there. That's like my new origin. The origin has gone right 2 and up, right 1 and up 2. Okay. If you want, you can even draw in a little dotted line now. Treat this like your asymptote. Like your x-axis. Okay, it's not an asymptote, it's an x-axis. The vertical line there, the vertical dashed line, is the asymptote. So from this point, now let's think about how we graph y equals log base 2 of x, all starting from this point right here. So we know that it goes through 1, 0 normally. Well, from this new origin, we go right 1, and there's our point at 1, 0. Normally, this logarithm curve goes right 2 and up 1, because the log base 2 of 1, log base 2 of 2 is 1. Okay, so we're going to go 2, 1. Again, I'm counting from the new origin. Then I'm going to go over 4 and up 2, because 2 is the exponent we put on 2 to get 4. Anyways, there's the graph there. That's the idea. Find your translated origin and graph from there. Okay, here we're going to go just down 3. Okay, so we have the same asymptote. Our asymptote is the y-axis here. 1, 2, 3, 4, 5. 2, 3, 4, 5. Label it up. Okay, but it's going to go down 3. So 1, 2, 3. Again, if you want, you can go ahead and put a little dotted line here. It's not part of the graph, but it's just kind of a helper line. That's like our new axis. This is like our new origin. So treat this as the origin, and let's graph y equals log base 3 of x. Okay, so that goes through 0, 1, 1, 0 actually, 3, 1, 9, 2, and then it's going to go down, down, down. Okay, so find that translated origin and draw your graph in. Let's move on to 4C. Okay, 4C here, we want to solve some problems with exponential functions. Okay, so given this function here, we want to determine if it's exponential growth or decay. That all is determined by the b value. So this is going to be exponential decay. And the reason is because 0.5 is less than 1. Okay, the b value is less than 1. This guy right here, looking at the b value, okay, this is going to be exponential growth. Now, even though it's in the negative direction there, we're still going to call this exponential growth. Okay, because 1.2, the b value, is greater than 1. Now we want an exponential function that goes through these 2 points here. Well, we want it just a simple y equals a times b to the x. So substitute 0 for x and 5 for y, and we get this, 0. And b to the 0 is just 1, so a is 5. Now we've got that a is 5, so we can find our b value. So we got y equals 5 b to the x, and let's substitute this 405, so let's put 4 in for x and 405 for y. So 5b to the 4th. Let's divide everything by 5, and we've got 81 equals b to the 4th. Take the 4th root there, and we have that b is 3. The 4th root of 81 is 3. So now we can write our function y equals 5 times b to the x. Nope, b in that case, we just found out what b is. B is 3. Okay? Don't forget to rewrite your function. Okay? One more, same idea. Plug in 2, 2, and 4, 8. Well, if we plug in 2, 2, we get y equals a b to the x. So we have 2 equals a b to the 2. All right, we could solve this for a, and that gives us a is 2 over b squared. Then we can plug in this other point here, and we know that y is 8 when x is 4. If we plug this guy into here, we get 8 equals 2 over b squared times b to the 4th. So 8 equals 2b to the 4th all over b squared. Well, these are going to cancel there, leaving us with, let's see, 8 equals 2b squared. So divide by 2, and b square root, b is 2. Okay? It could be 2 or negative 2, actually, but b cannot be a negative number. So if b is 2, we can come all the way back over here, plug that in, and we see that a is 2 over 2 squared, which is 2 over 4, which is 1/2. And so our function y equals 1/2 times 2 to the x. Okay? All right. Solving exponential equations, we want to we want to take the logarithm, basically, unless we can find a common common base. Now, 216 is really 6 to the 3rd. So we have 6 to the 3rd to the x minus 5. And let's rewrite 36. Well, that's 6 squared to the x plus 2. You want to be familiar that 216 is 6 to the 3rd power. Now we're going to multiply these. This is 6 to the 3 times x minus 5. Power to power, we multiply. This is 6 squared to the x plus 2. And since we have a common base here, we can say that these guys here, these exponents are the same. So 3 times x minus 5 equals 2 times x plus 2. Okay, and so that's 3x minus 15 equals 2x plus 4. Solve that up, subtract 3x, add 15, we get x is 19. Okay? Over here, you want to subtract 8 from both sides first. We get 3 to the 2x plus 1 equals 27. We can rewrite this 27 as 3 to the 3rd power. And so now we know that 2x plus 1 equals 3. Subtract 1, divide by 2, we see that x equals 1. Okay? Another way you can do this is you could take the log of both sides. We could come back here, we could say take the log of this and the log of this. We can take that exponent down there. Okay, this is going to get a little uglier, but it works. Log 3 equals log 27. And if you divide both sides by log 3 here, squeeze in there, okay. If you divide both sides by log 3 and you go to your calculator and figure out what this is actually going to give you 3. Log of 27 divided by log of 3 is 3. And that'll put you right to here, which gives you the same answer. Okay? Here, 5 to the x, well, this 625 is 5 to the 4th. And so that is, another way to write that is 5 to the x equals 5 to the negative 4. And so x is negative 4. Okay. Last but not least, could this be an exponential function? Well, we got to check the factors here, the difference, the quotients. 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 2, or 8 divided by 4 is 2. We have a constant multiple there. We're multiplying by 2 times 2 times 2. So yes, okay, we have a constant multiple of 2, or actually, yeah, that's fine, constant multiple of 2. Okay. All right. What's a better way? I just don't like that multiple here. Probably a better way to say that would be it's not a constant multiple, it's a constant ratio is what it is. That's a better way to say it. Okay. Next, we're going to go on to logarithmic equations. All right, here we are on section 4D, and we're in the car driving home with the family. Say hi, family.
Hi, family.
And so here's some answers for 4D. So we got to solve these logarithmic equations. So we have several methods that work. With this one, we have a single logarithm. So just use the definition, swing the base around. We have 3 squared equals the square root of x minus 2. And so the square root of x minus 2 is 9. That's pretty simple. Then we're going to square both sides to get rid of that exponent. Like I said, I'm in the car, so sorry if my handwriting's bad. Then we've got x minus 2 equals 81. Add 2, we get 83. When you're dealing with logarithmic equations, always plug it back in to see if that solution causes a problem with the domain. So 83 is just fine. Plug in 83, all comes out to be positive. And remember, the domain of logarithm is that you have to have positive numbers in there. All right, 22 here. Well, similar situation. We got a single logarithm all by itself over there. But we've got to get that logarithm all by itself. Subtract 5, natural log of 0.02x equals negative 10. This is base E, remember. So we got 0.02x equals e to the negative 10. Okay? And now let's divide this by 0.02. Okay? And so x equals, that's e to the negative 10. We could drop that down to the bottom, and we could say 1 over 0.02 e to the 10th. Okay? Or if you want to make this a little cleaner, you can multiply top and bottom by 100, because I don't like that decimal down there. And we could write it as 100 over 2e to the 10th, which is actually 50e to the 10th. Oh, 50 over e to the 10th. Okay, so there's our exact answer there. If we want a decimal approximate, we can plug that in our calculator, but we'll leave it there for now. All right, going to 23 here. Again, simple logarithm. Just use the definition. Swing that base around. X equals 6 to the negative 4th. Well, that's just x equals 1 over 6 to the 4th. And 6 to the 4th is 36 squared. So we got 1296, thanks to my son Caleb, who helped me work it out. All right, so there's our answer. Simplify it, leave it alone, there you go. Okay, next guy here, we've got an exponential. Okay, not a logarithm, but we're going to use our logarithms. Let's divide by 3, and we get 8 to the x equals 50/3. Okay, now what we need to do is we need to take the log here. I'm going to take the log of both sides. And so let's take the log of this and the log of this, squeeze it in there. Okay, we're going to drop the x down. We have x equals, nope, let's back that up. We have x times log of 8 equals log of 50/3. Okay, and then we're going to divide by log of 8. Divide by log of 8. Okay, and so x equals log of 50/3 all over log of 8. Okay, there's our exact answer, and we can approximate that with our calculator. All right, so that is approximately 1.35 according to our calculator. All right, a few more here. Let's evaluate this guy. Log base 4 of 12, and well, we can use our change of base is what we need. Change of base formula says that's log of 12 divided by log of 4. Notice that 12 is not a power of 4, so we got to use that. So that's about 1.79. Okay, and yes, you need to show this in between step there. Okay, all right, here, same story. We have the log of 26 all over the log of 1/3. That's our change of base formula. And that is about negative 2.97. Okay. I want to put these together as a single logarithm, so we're going to put this guy up top. When we first get those exponents up, log base 3 of x squared plus, put the 4 up top there, log base 3 of y to the 4th minus log base 3 of z cubed. Okay, now we can put these two together. This is going to be the same as multiplication. So this is log base 3 of x squared y to the 4th minus log base 3 of z cubed. Okay, and now subtraction becomes division, and so we have log base 3 of x squared y to the 4th all over z cubed. There you have it. Okay. This guy right here, put this up top. We've got log base x of w to the 4th plus log base x of y to the 6th. That's addition, so let's put them together. We got log base x of w to the 4th y to the 6th, and that's all we can do with it. Okay, gonna now break these up. Gotta watch out here for this guy. We've got log base 2. We'll do some subtraction here. Log base 2 of a squared b cubed. Now we've got to break this up, but watch out because of this subtraction here. We've got log base 2 of x squared minus, and put some parentheses here, log base 2 of a squared plus log base 2 of b cubed. This negative here is going to get distributed out there, and we're going to drop these exponents to log base 2 of x minus 2 log base 2 of a. Again, this minus affects both of these, so we're going to have minus, bringing this exponent down, 3 log base 2 of b. There's the expanded version. And one more here. Break it up. We got log base 2. Break up the multiplication here first. X minus 2 to the 5th plus log base 2 of 4x cubed. Okay. Now drop the exponents. 5 log base 2 of x minus 2 plus 3 log base 2 of 4x. And then, nice, log base 2 of x minus 2. This guy we've got to break up. We're going to have 3 times log base 2 of 4 plus log base 2 of x. And last but not least, we're going to break this up, distribute that 3 to clean it up. And we have 5 log base 2 of x minus 2 plus 3 log base 2 of 4 plus 3 log base 2 of x. There is our solution there. Alright, last problem we're going to substitute here for A is the amount we want, P is what we start with, R is the rate as a percent, 0.043, and T is time. We want to solve it for time, so we're going to divide by 250, and we get 3 equals e to the 0.043t. Now we're going to take the log, we're just going to change this to the natural log form, so that's a natural log of 3. Swing this e around to the bottom, it's base e, 0.043t. And now let's divide by 0.043, divide by 0.043. And so time, I'm just going to calculate natural log of 3 divided by 0.043. And that gives us approximately 25.5 years. Okay, there you have it. Okay, that's how we work with our logarithms, solving those equations. So good luck, work hard.